Let's start with something simple. The cat chased the dog. The dog chased the cat. Same words, totally different meaning. But here's the problem. To a neural network, both look like just a list of numbers. It doesn't see order. It only sees vectors. So how does a model tell the difference between those two sentences? That's what we are exploring today. The hidden magic of positional embeddings. They are what let transformers understand that order matters. In this session, we learn how words become embeddings, the numbers that capture the meaning. For example, cat maps to this array, or dog maps to this array, or chase map actually to this array. Cool, but if you take those three embeddings, cat, chase, dog, and shuffle them around, the model cannot tell which came first. It might think that dog chased the cat and cat chased the dog. They are the same meaning. And that's a big problem because language lives in order. So we need to somehow tell the model, hey, this word came before that one. This is the first word, this is the last word. And basically, we need to give the model a sense of position. That's what positional embeddings do. They're like tiny timestamps for every word, telling the transformer where each token belongs in a sentence. Older models like recursive neural network or long short-term memories handle order naturally. They process words one by one, step by step. But that made them slow, and they struggled with long sentences. Transformers changed the game. They read all the words in parallel, super fast, super scalable, but by doing that, they lost their sense of sequence. The fix is clever. For each token, we add a position vector, a set of numbers that says, I'm the first, I'm the second, and so on. Mathematically, it's simple. You have the x, for example, is the token embedding plus positional embedding, just vector addition. But that tiny trick gives the model a map of word order. Now there are two main ways to create these position vectors. Option 1 is learn positional embeddings. Each position, 1, 2, 3, 4, gets its own variable vector, just like each word gets an embedding. It's simple, it works well, but only knows position it's seen during the training. If you train it to sequences up to 512 tokens, it won't generalize well to 1024. Option 2, however, is sinusoidal embedding. Introduced in original Attention is All You Need paper. Instead of learning the positions, we generate them using sine and cosine waves. Why sine and cosine, you may ask? Because they are smooth, they're continuous, and they are periodic. They're perfect for expressing gradual changes across the sequence. They let the model extrapolate to a longer sentences it's never seen before. Here is what the sinusoidal formula looks like. You have pos, which is the position of first word, second word, etc. You have I, which is the dimension index, and the D in the formula is the total embedding dimension. Looks abstract, so let's plug in some numbers here. Let's say our embedding dimension is 4, and we are looking at a token in position of the 3. Then for the first dimension, we have this answer, 0.14. For the cosine wave, we have minus 0.99. For the next pair of dimensions of I equal to 1, you have sinusoidal value of the 0.03 and the cosine value of the 0.999. So the positional vector for position 3 looks roughly like this. Each dimension oscillates at a different frequency. That's what makes every position unique, a distinct pattern of sines and cosines. So to understand this, imagine each embedding dimension like a wave channel. Some oscillate quickly, some slowly. Together they form a complex pattern, a unique wave signature for every position. And here's the cool part. If you're coming from the electric engineering background, especially the telecommunication, you may have the feeling of a Fourier transform here. In the signal processing, the Fourier transform says that the complex signal can be built by adding up sine and cosine waves. And each of those sine and cosine waves, there are different frequencies. Sinusoidal positional embeddings do the same thing. They use a mix of high and low frequencies to represent each position at the sum of the simple oscillations. So when you compare them, for example, position 3 and position 4, they have the similar patterns. Their waves are almost in sync, but position 100 totally out of the phase, a completely different wave signatures. Just like sound waves can interfere, for example, constructively or destructively, the transformer can also tell how far apart two tokens are. It can achieve this by comparing their wave phases. It's like the model is performing the mini Fourier analysis. It is not just reading the words. It's hearing the rhythm and spacing that tie them together. Let's make it concrete. Take the sentence, The sun rises in the east. Each word has two parts, its meaning and its position. For example, this table, you can see token, meaning, position, and combine arrays for this sentence. When we add position info, the model understands that sun comes before the rises and east comes at the end. That is how transformers read in order, even though they process it in parallel. Modern models, however, they take it further. Instead of absolute positions like first, second, and third, they use relative positions, how far apart tokens are. This is where rotary positional embeddings or ROPE comes in. It is used in models like Llama and GPT Neo X. They rotate the token vectors in complex space, encoding the angle between positions. This gives transformers a better sense of distance, and it helps them to handle the longer context without breaking down. We will unpack RP later in this series, but keep it in mind. It is the next evolution of positional encoding. Without positional embeddings, a transformer wouldn't know that dog chase cat is different from cat chase dog. With them, the model gains a sense of sequence. It understands a structure, syntax, and order. That's what turns random tokens into language, and language into the meaning. If you like this series, don't forget to like the video and subscribe to the channel. And if you have any questions, don't forget to comment it down below. Until the next video, good morning and good afternoon and good evening. Bye.